All right, today we're going to go over thermodynamic processes, pressure, and kinetic molecular theory. After this, we're actually going to go directly into the review. There's an assignment posted on Canvas right after it. It's titled Thermo in-Class Practice. I'm going to go ahead and throw this on this video, and I'll also link the video on that assignment in case you missed it. And then I'll just have you go to the end of this video to do so. It's essentially additional notes. We want to do some practice problems. I just didn't have them in the actual slideshow, so I threw them into a worksheet. And so we will do them there. So the first thing we need to talk about is pressure. Just so you have an idea of what pressure is, there's some equations, there is some like math terminology. We are not going to get into that. A lot of what we're going to talk about today, we are just going to skim the surface. We're not going to get super deep. I'm going to tell you to ignore some things today because we don't have time to get deep. And in fact, we don't have the knowledge yet to get deep because we haven't talked about energy yet. That's a big no. I wish we had talked about energy first. Unfortunately, we just can't do thermo without talking about energy first. But unfortunately, also, our school district decided to say, hey, we should do thermodynamics before energy. Whatever. It's better for y'all because we want it to go as deep. So we want to have as harder problems. So pressure is the force applied over an area. Think about your tire pressures. In your car, you have a tire, and that tire has a bunch of air in it, and it's forcing air out on the tire, on the rubber, and that's what keeps your tire, strong. And so it's a force over the area of the inside of your tire. It's a force over an area, which is what we have written here. Force over an area. We don't actually have to do any math with this. I just need you to understand what pressure is. You need to understand what pressure means. Think about if you blow up a balloon. If you blow a balloon, you are putting air pressure in there, and it's putting more pressure on the inside of that rubber balloon and forcing it out. You're applying a force over an area. There's a bunch of different units. We're going to focus on Pascal. That is our SI unit. And so it's abbreviated as PA. But you're going to hear a bunch of other ones, although I'm going to do my best to make sure none of the worksheets have conversions that we have to do with this. But in case you see them, we have PSI, we have atmospheric pressure, we have something called a bar. We also have mmHg and torr. There's a lot of different units. They're all right here. Okay. And so imagine we are enclosing a gas in a box. And if we put more gas into it, there's more pressure. If we take out gas, we're going to have less pressure. And overall, that's the idea of what we're doing. We're going to be talking about a lot of gases today in an enclosed space. And then lastly, we need to make sure we reference this equation. Delta U equals Q minus the work, where delta U is our internal energy. Q is our heat added to a system, and work is the work done by a system. Okay. So here's the first start of the processes. Before we talk about that, let's talk about what a process is. All we're saying is, hey, we have some gas in a box, and I'm going to do something to it. Maybe I'll push down on a piston. Maybe I'll add some heat to it. Maybe I will expand it so it has more volume. I don't know. I just want to do something to my system, right? And so if I do something to it, it's a process. It's all processes is you're doing something. And so we have a bunch of different names depending on what we do. We have an isothermal process. An isothermal process means iso means the same, and thermal, as you can probably guess, refers to temperature. And so an isothermal process is one where the temperature remains the same. Our temperature does not change. When we talk about these processes, you need to know three things. You need to know, one, their definition. So we just talked about the definition. Great. You need to know, two, you need to know their graph. And so we'll talk about the graph in a second. And then three, you need to know how they relate to our delta U equals Q minus W equation. And we'll talk about that at the very end. We'll talk about them all at the same time. The graph here, we graph it by graphing some sort of curve. It looks like the inverse of x curve. So if you remember this curve from algebra, y equals 1 over x. Remember that this curve looked kind of like this. All of our isothermal processes will have a similar looking curve to that, okay? So they should always be graphed like that. Depending on what your temperature is, it's going to either be lower or higher. So you can see here we have a higher T, and so our curve is more outside, while our lower T is more inside. If we want, just so you know, I'm not going to test you on this, but in case you're curious, if we want an isothermal process, we got to have some sort of thermal reservoir. Because as we push in on a gas, I don't know if you've ever like compressed certain shapes and you've gotten some heat. As we press an ideal gas, we're actually going to change the temperature by compressing it. Or we might, release temperature. And so in order to actually keep things the same temperature, we have to have some sort of reservoir where we're either giving heat or taking away heat. We have to do it slowly so that we can actually adjust the temperature in order to keep it the same temperature. Okay. We have an adiabatic process. What does adiabatic mean? This is the weirder one, sounding one. It means that no heat flow in or out of the system. So it means that Q is equal to 0. Remember, Q is our heat. Okay? So it means that no actual energy is entering or leaving our system, in the form of heat at least. And it actually has a very similar curve to isothermal. And so you will never be expected to identify the difference of them on a graph. They will be labeled for you. It'll tell you whether it's isothermal or not on the graph. Okay? Or you will find it out. There will be some extra information given to you. Like I will say, hey, in this process, Q equals 0. So what kind of process is it? Oh, well, it's adiabatic, because that's what you just told me. Q equals 0. I'm going to turn off my notifications real quick. Great. So an adiabatic process means that if Q equals 0, it means that energy is only transferred by work, right? So if we have some sort of transfer of energy, if Q is equal to 0, that means the only transfer of energy is through work, right? Q equals 0, so we just exit off. We could get more complex in this. That's all you need to know. You need to know that delta U is equal to negative W. We also have isobaric. These processes are a little bit more simple. Isobaric means that we have the same pressure. So the iso means same, baric means pressure. Remember that bar was one of the units for pressure. That's not the one you were using. We're using Pascal whenever we talk about things, but bar is one of them. And bar comes from that same root about pressure. And so isobaric means same pressure. And we also have isovolumetric, also known as isochoric. You need to know both terms. And that means, well, isovolumetric, same volume, means constant volume, right? And so again, on these PV graphs, this is where the curve makes a bit more sense. If we have constant pressure, P is our y-axis, which means if we have constant pressure, we shouldn't be changing our y-axis. We should just moving left and right. We shouldn't be moving up or down. And so that's what this is. Isobaric means we just have a straight horizontal line. Similarly, if we have constant volume, volume is our x-axis, which means our x-axis should not be changing at all. We should not be moving left or right during our graph. We should just be moving up and down. And so isovolumetric means that we have a straight up and down line. Okay. And you need to know, again, we're not going to do any of the math, but you need to know essentially that if we have isobaric, it means that our change in pressure is 0, like we just discussed. There is no change in pressure. And so the key here is that the work is equal to P delta V. You just need to know that fact. We're not going to do any of the math with it necessarily. We might do a little bit. And then isochoric, you just need to know that means the change in volume is 0, which means that the work done is 0. You need to know that W equals 0 in that case. Okay. And so here's what it kind of looks like if we put them all together. We could have some sort of process from A to B. That's isothermal. We can change our volume by changing our pressure while keeping the temperature the same. But then if we want to keep our pressure the same but decrease our volume, we can go from B to D. But in that case, if we're keeping pressure the same, we're going to have to lower our temperature. And then if we want to go back D to A, we can do that. But if we're going to do that with constant volume here, and we're going to increase our pressure, we're also going to have to increase our temperature in order to do that. Lastly, work done on a gas is equal to the area under the PV curve. I'm actually not going to test you on this. We could try to make it happen. And some of the work she's going to talk about it. And so if you're like, I really like physics, I want to get into it, you can totally do it and you can totally figure it out and answer some of those questions with this knowledge. The work done is equal to the area under the PV curve for every single process. And so if you look at this process compared to this process, you could tell that, okay, the area under this curve is a lot less than the area under this curve. Therefore, this is doing more work than this. However, I'm not going to test you on this. In fact, I took off the problems off the assignment, like the in-class practice, as well as the homework assignment that talked about work. We're not going to get super deep into that. We haven't talked about work yet. We need to do energy first. We will talk about work when we get to energy, though. Okay. And so we talked about three things again. One, you knew your definition. We talked about all the definitions of the four processes: isothermal, isobaric, isovolumetric, and adiabatic. We talked about the graphs. Isothermal was something like that. Isobaric was constant pressure, so we went horizontal. Isovolumetric was vertical, and adiabatic was also like that. It just looked a little bit different. Again, you are not expected to know the difference between these two graphically. You would have to tell the difference with some extra information. Okay? And then 3, you need to know what the first law predicts, given this information. And so I'm going to box it off. Isothermal means that we have no change in internal energy. Therefore, you need to know that Q is equal to W. And so I don't know if this is in your fill in the blank notes. You should write it down separately. You need to know isothermal implies that Q is equal to W. The heat entering the system is equal to the work done by the system. If we have constant pressure, you need to know that thing where we talk about W is equal to P delta V. That's basically it. W equals P delta V. Okay. You need to know if we have isovolumetric, that means the work is equal to 0. And so, again, given that equation, delta U is equal to Q minus work. If work is 0, that just means that Q is equal to delta U. That just means that these are to equal because this is 0. And lastly, if Q is equal to 0, again, given that same equation, Q is equal to 0, scratch it off, delta V is just equal to negative W. Okay. So these are the things you need to know for each one. So if you need to make a little graphic organizer, this is a great one right here. Although I think this side is a little bit messy. So you just need to know the things I boxed off. Q equals W, W equals P delta V, Q equals delta U, and then delta U equals negative W, going down that list. And let's see if we can move on the slide. Okay, we have something called the ideal gas law. It's this relationship that the pressure and volume are proportional to T. But how are they proportional? We got to figure that out. Okay. One thing we need to talk about is something called a mole. Hopefully you study this in chemistry a little bit. A mole is equal to the number of grams of a substance that is numerically equal to the molecular mass of the substance. I will not expect you to do any of the molar calculations by using, Avogadro number. We're not going to deal with any of that today. That's just out of my course. I don't really care to do that, okay? We're not going to deal with that. I will give you N or N is something you're solving for. It's not going to be something you have to use this equation for. So don't worry too much about it if you don't remember any of your molar work. We're not going to deal too deeply into it. What you do need to know is you need to know this equation. PV equals nRT, where P and V are our pressure and volume. T is our temperature. So these are things familiar to us. N is just the number of moles in something, which is, again, I'm going to just tell you in a problem, hey, there's this many moles, or maybe I say, hey, what's the amount of moles in the substance? it's not going to be something we have to do extra work for. And then R is just a constant. R is equal to this. And again, I'm not going to try to do some confusion by converting units. We're always going to use that number. There are other things, depending on what pressure we're talking about or what energy we're talking about. We're not going to deal with them. That's our R every time, 8.315. If you want to write this in, just for completion's sake, you can, but we're not going to talk about Avogadro's number. You guys were studying last year. We're done. We're not going to worry about it. And so this is a different way we can write it if we wanted to use Avogadro's number with a capital N. But again, let's not do it. And we're also not going to really talk about kinetic negative theory. So we're not going to worry about this either. So cool. If you want to write this down, fill in your notes, you can. Otherwise, we're going to move on. We are going to now move to the assignment. Okay. So make sure you have the assignment out. We're going to work on it together. If you can print it, great. If not, just have the assignment on your screen somewhere or something. Or I'm just going to work it on here and have some paper to work with me. So let's say we have a cylinder that contains 2 moles of something, of a gas. It's initially in state A with a volume of that and a pressure of that. The gas is brought isobarically to state B, where the volume is this. Then the gas is brought to a constant volume to state C, where its temperature is that. And then it's brought in the same temperature as state A. And then the gas is brought isothermically back to state A. So what's happening here is we have 3 different, we're going from A to B, then B to C, then C back to A. So we have 3 different processes. And essentially we have 3 different states. So when I work these problems, I'm just going to organize my work. Do a T-chart or just do what I do. Just label A, B, and C. And easily, we're not adding or removing substances from each of these. And so we can figure out N and R really easily for all 3 of these. We're told the number of moles is 2. And R is always this. Okay. 315, right? The real challenge is P, V, T. Those are the other 3 knowns that we need to know and try to figure out for everything, potentially. We may not need all this information, but I'm just going to be thorough for today because I want to show you kind of the whole process. Okay, so we have 3 states and figure this out. What are we actually trying to figure? Let's try to find the pressure of the gas at state C. So we need to find pressure here. In order to find pressure there, we need to use this equation. And in order to solve this for P, we need everything else. We need V, we need N, we need R, we need T. So we need to find V and T. So what information do we know about V and T? Well, we know the temperature is the same temperature as state A. State C, where its temperature is the same as state A. So if we can find this temperature, that means we know this temperature, right? And then we also are told that the gas is brought isobarically. No. Where the gas brought a constant volume to state C. And so from B to C, we have the same volume. And so if we can find this volume here, we can find that volume. So let's go through all the positions. In state A, we have a volume of 1 times 10 to the negative 2 and a pressure of 4 times 10 to the 5th. Well, looking there, we have everything we need in state A to find temperature, which means that we can find the temperature for C. If we look at B, we know that the gas is brought isobarically to pressure state B. Isobaric means the pressure is the same. So it means that A and B, the pressures are the same. So we can write that in for free. And it tells us the volume at B is 2 times 10 to the negative 2. Which is nice because we needed that volume for C. We concluded, because the gas brought a constant volume to state C, that our volume is going to stay the same. So all we need to do is we need to do this to find T, and then once we had to, we can use it to find P on this side. So PV equals nRT. If we want to solve for T, we should divide by N and R on both sides. So T is equal to PV over NR. If you're not so hip on your algebra, go ahead and write this down if you would like to. T is equal to PV over N equals R. NR over NR. And so let's go ahead and type this in the calculator. P is 4 times 10 to the 5th. And then V is 1 times 10 to the negative 2. And then it's divided by 2 divided by 8.315. Cool. We get a number like this, 240.5 Kelvin. Our temperature is always in Kelvin. And again, we were told that our temperature in A is the same as temperature in C. So now we can use that to find P. Using this equation, we can divide by V on both sides to get P. So P is equal to nRT divided by V. So let's take 2 times 8.315 times our temperature, which we just found, and then divide by our volume, which is 2 times 10 to the negative 2. Make sure that you have all this in parentheses when you divide by it, because so your pressure should end up with 200,000. Or if we want to continue the pattern of scientific notation, we can go ahead and do 2 times 10 to the 5th. Then it says on the axis, state B to represent, or state B is represented by the point B here. So remember that our B, we had the volume of 2, and we didn't, and the pressure was 4, right? So 2, 4. And it wants us to sketch a graph of the complete cycle. So basically, we want to label points A and C. What was A? A was pressure was P4 and volume was 1. So let's write that. Volume was 4. Pressure was 4. Volume was 1. So right there, right? Pressure is 4. Volume 1. That point, that was A. And what was C? C was pressure was 2. Volume was 2. So let's find that point. 2, 2. And we know A to B goes there, which should make sense because A to B was isobaric, right? And so it should have been horizontal. And then B to C was isovolumetric because we said we had the same volume. And so if we want to get back from C to A, we're going to go ahead and draw a curved line there because we need to do isothermal. And the curve is always looking like it's always has to represent a 1 over x curve. It's always got to be curved like that. We're skipping C and we're skipping D. If you want to know the answers, I can go ahead and tell you. The answer is positive here. And then the answer is heat engine. But we're not going to worry about those. Okay. So this one, it's going to be a little bit trickier, but we're still going to be able to do it. Although we're not going to do most of the problems here. I think we're just going to do A, maybe B. We'll see. Okay. So in this one, we want to try to find the pressure. We are told a few things. We're told that the volume increases to 2V from A to B. We're told that we keep constant temperature. And of course, N and R and T are all the same. And so when we look at this, N and R are always the same. And T apparently is being the same, right? So A, the process AB is constant temperature. And so that T is staying the same. So overall, this whole thing is staying constant. So if we think about that, let's just say that it's equal to 1, right? It's some number. I don't know what the number is. It's some constant number. Let's say 1. Why not? If P is going to increase, okay? Right? Let's say P, it goes from 1 to 2. So we have this equation 1 times V equals 1, and then 2V equals 1. If P increases, that's got to mean that V is going to decrease by that same amount, right? It's got to decrease, but by proportionally, it's got to 1/2. Because here, in this case, 1 times V is equal to 1. That means V is 1. But in this case, 2 times V equals 1 means that V has to be 1/2. So if this is staying constant, the amount that P increases is the amount that V has to decrease because they're inversely proportional. So I say all that because now our question is saying that during the process AB, pressure A is P naught. Determine the pressure at B given that the gas increases from V naught to 2V naught. So again, PV equals nRT. In this case, volume is increasing by double, right? Volume is increasing by 2, which must mean that P is halved. So if the pressure at A is P naught, that must mean the pressure at B is 1/2 P naught. Okay, we can also do B. B asks us during the process AB, what's the work done by the gas? Well, let's look at the process AB. AB is constant temperature. AB is isothermal. Which means what? It means that delta U equals 0, which meant that Q is equal to W. So the work is equal to the heat. Was there any information about the heat? Well, if we read, it says that the gas absorbs 1,000 joules of heat. So the work is equal to 1,000 joules. It's pretty simple as long as you can go through the steps and go through the terminology. What's the process AB? What kind of process is that? What does that mean for me? What does that mean for me about my heat? What does that mean for me about my work? What information do we have? There's no math involved here. It was just reading and knowing our information and drawing a conclusion. We're going to skip C. We're going to skip D and skip E. There's a lot we're going to skip. It's a bigger worksheet. We're going to skip a lot of them. The homework assignment, there's less to skip, and so you'll get more practice there. Okay. A cylinder with a movable frictionless piston contains an ideal gas that is initially in state 1. So we're starting here at 1. Let me go ahead and write that down. 1, we have a pressure of 1 times 10 to the 5th. We have a temperature of 373 Kelvin. And we have a volume of 0.25 meters cubed. So Pascal. Okay. The gas is taken through a reversible thermodynamic cycle as shown in PV diagram above. So I'm going to teach you something real quick right here. So that's why this is part of our notes. I messed up. Whatever. P is equal to 1 times 10 to the 5th again. V is equal to 0.25. And then T is equal to 373. Okay. If we're not adding moles or anything, so N and R are staying the same, a little shortcut we can do is because N and R are unknown and they're staying the same throughout the entire process, we can just go ahead and shortcut this and just say PV equals T. Okay? And that's totally fine. We're allowed to do that. Then, process 2. Let's see what happens in state 2. When we go from state 1 to state 2, guess what's happening? We're increasing our volume. We're going from 0.25 to 0.5. So if we just read the graph, we get a new volume, 0.5. And if we also look at the graph, our pressure is staying the same. Our pressure is also 1 times 10 to the 5th. So our temperature is something we can just find really easily. We just use PV equals T. That means T is just equal to the multiplication of the two. Actually, I should say, let me rewrite everything I just said. Take it back. It's not that PV equals T. It means that PV over T is equal to PV over T. So our pressure, volume over temperature that we have in our initial state 1 is equal to our PV over T in our state 2. Okay. And so let's see how that works. Pressure times volume over 373 is going to be equal to our pressure times volume over our temperature in state 2. We're just looking at state 1 and state 2, PV over T for both. And how do we solve for T? Well, let's first simplify it. So let's simplify the top and bottom of each. 1 times 10 to the 5th times 0.25. We're going to get 25,000 over 373 is equal to 1 times 10 to the 5th times 0.5 should give us 50,000, yep, over temperature. And look, this is just a cross multiplication problem. If you don't remember how to do that, do your bat and ball, multiply 50,000 times 373, and then divide by 25,000, which is essentially just 373 times 2. And we get our temperature is equal to 746 Kelvin. At state 3, we have, what information do we have? We have pressure. Let me clear the board because I'm running, it's not wanting to write. Okay. At state, let's look at state 1 again because we know all that information. P equals 1 times 10 to the 5th. V equals 0.25 and temperature equals 373. Again, at state 3, we know, reading the graph, pressure is now 1.5 times 10 to the 5th. Temperature is what we're looking for, and volume is, according to that graph, 0.25. So we can do the same thing. PV over T is equal to PV over T for the two different states. This is state 1, this is state 2, or in this case, state 3, I mean. PV 1 times 10 to the 5th times 0.25 all over 373 is going to be equal to 1.5 times 10 to the 5th times 0.25 all over 373. So 1 times 10 to the 5th times 0.25 should be the same thing we got last time of 25,000 divided by 373. That's a 3. And then 1.5 times 10 to the 5th times 0.25 is 375 over T. That should be T, my bad, right? We don't know that T on the 3 side. That's what we're looking for. So again, we do the bat and ball trick. Multiply 37500 times 373 and then divide by 25,000 and we get 559.5 degrees. Or in this case, it's actually Kelvin. Okay. Again, no net work. We don't need to find heat. And so we are done with that worksheet. And so the rest I will leave to you. That's the homework assignment. Let me know if you have any questions on it. You should, based on the notes, be able to gather how you do it. You can also Google those questions. If you Google them or like copy and paste them into Google, there are answers online. I pulled the assignment from somewhere online. And so if you really need help, you should be able to Google those questions to get help. With that, I am done. Have a good day.